minus alpha square, or R12 equals plus minus I alpha. I is square root from minus 1. I is square root from minus 1. Now from here, solution is R square equals alpha square. So R 3/4 then equals plus minus alpha. So we have 4 roots. This characteristic equation has 4 roots. 2 purely imaginary and 2 real. You may want to write, our differential equation has 2 purely imaginary roots and 2 real roots. Okay, then we get, I will substitute. I was looking for C in power Rx. I found that R, there are 4 kind of R's. Okay, this restaurant actually serves, a full dinner contains 4 courses. Okay, so then this dinner is combination of C1 in power plus I alpha x, and minus I alpha x, in power alpha x, in power minus alpha x. Look, please, at least we have a clue how W of x should look like. We still don't know alpha, so because I don't know alpha, I cannot really substitute and calculate it. Also, I don't know C1, C2, C3, C4, but we will get to them. Any questions? Any questions? Please ask some question. Any question? No, say it again. These coefficients, no, these coefficients are constants. Because look, this is C times E in power Rx. So that is a constant. When we talked about, thank you for asking this question. When we talk about variable coefficients, we meant this one. That this coefficient EI rho A could be variable. But now we already said for us they are constant. E constant, rho constant, A constant, I constant. So these coefficients are constants. Now these guys, C's, are called, they are called constants of integration. And as the name suggests, constants are not variable because they are constants. Yeah, look, please. We will deal a lot with variable cross-sections and variable things. But in order to grasp that more complex, we should first understand what should we expect when things are constant. What is under ideal situation? Okay. Yes, of course, your question is very good. Okay. Because of this, then solution is like this. Solution. It can be written as it is here. I mean, look, please. It can be left as it is like this. C1 in power alpha x, C2 in power minus I alpha x, C3 in power alpha x, C4 in power minus alpha x. Or could be dealt with like this. B1 sine alpha x, B2 cosine alpha x, that is instead of these two guys. And here, hyperbolic sine alpha x, hyperbolic cosine alpha x. Look, please, that indeed is like this. Because, do you want me to derive this or not? Or we know this? Derive, okay, I'll derive this. So, look please. We will have W of x equals C1. Now I'm using Euler's formula. Cosine alpha x plus I sine alpha x plus C2 cosine alpha x minus I sine alpha x. Now plus C3. Okay, let us leave this C3 first. Alpha x plus C4 in power alpha x. So then we get W of x equals cosine alpha x times, so here is cosine and here is cosine, C1 plus C2. Then there is sine alpha x. Will be C1i plus C minus C2i sine alpha x. Okay, so I call this B1 plus these terms, yes? C3e alpha x plus C4e minus alpha x. And this is B2. So capital W of x equals B1 sine alpha x plus B2 cosine alpha x. Now plus, let us call this m plus, okay, this C3, I will call it m plus n in power alpha x, plus this guy I will call m minus n in power minus alpha x. Okay, C3 I will write as m plus n, and this I will write C4 m minus n. I'm allowed, because it's up in, I'm allowed to do this. I want to go to another set of constants. So we will have B1 sine alpha x plus B2 cosine alpha x plus the in power alpha x, no, plus m. And m will be in power alpha x. Yeah, okay, sorry, I would like to write m plus n divided by 2, n minus n divided by 2. That is what I want. I realize that I want only half an ice cream because it's too many calories. Okay, so I'm getting plus m, then we get in power alpha x plus in power minus alpha x divided by 2. Then plus n in power alpha x minus in power minus alpha x divided by 2. Okay. Now this is hyperbolic sine. This is hyperbolic cosine. Okay, and then just so this I will call B3, and this I will call B4. Because I want to call things B1, B2, B3, B4. Can I get rid of this sheet of paper? So we will deal with the second one, but then we also will deal with something more, even more convenient. First of all, I don't want to have i's in power I, etc. I don't like this. So I like sines and cosines. Then I don't like e in power alpha x's. I like hyperbolic sines and hyperbolic cosines. Now I'm modifying my desires. Okay? Yes. Okay, so this we don't need actually. They derive this here. I hope I will find what I'm looking for. So we will write this, okay, in a different form actually. Totally different form now. I will show you. Yes. Yes. So we will write it as follows. Look, please. A1 K1 alpha x. I will explain what it is. A2 K2 alpha x. A3 K3 alpha x plus A4 K4 alpha x. Before that I had B, but now I wrote A. It's okay. And these functions are most convenient. And I will write down these functions. I wrote this from my book, so and copied. I did not find the transfer. So now I do a combinations actually. I can do combinations of these functions. Okay, I have, look please, I have sines, cosines, hyperbolic sine, hyperbolic cosines. I would like also to make combinations of these functions so that we will have hyperbolic cosine plus cosine and it takes 1/2. 1/2 hyperbolic sine plus sine, hyperbolic cosine minus cosine, hyperbolic sine minus sine. We can also derive this very easily just by changing, we can actually introduce some, instead of B1, B2, B3, B4, we can just rearrange this and write like this. It's very easy. So we have these 4 functions. Now, these functions are denoted as K functions. K functions. So they are called Krylov functions. Someone from Russia by name Krylov, ocean engineer, introduced these functions many years ago, but in 20th century. He said that these functions are most convenient for beam vibrations, not any other functions. Now, these functions have very nice characteristic. Pay attention what kind of characteristics they have. K, let us calculate K at 0. How much is K at 0? No. K at 0 is 1, because hyperbolic cosine is 1, this is 1, 1 plus 1 divided by 2 is 1. Now, how much is this one at 0? 0. How much is this one at 0? 0. And how much is this one at 0? 0. Now let us calculate the first derivative of k1. Just calculate. I would like you to differentiate k1 and tell me differential of k1, derivative, how much it is. No, I did not ask you derivative at 0. I want derivative of k1 with respect to x. What is that? No. I would like you to tell me in terms of k's. We have 4 functions, k1, k2, k, yes? Negative k2, why? Okay, let us talk derivative in the beginning, how much it is. Okay, let us calculate first derivative of this function, how much it is. First derivative of k2. How much is the first derivative of k2? Maybe that's an easier question. No. If you start with half, then it is wrong. No, not half. Why half? Oh, alpha, yes. Derivative of this, of k2, is alpha times k1. Now, how much is derivative of k3? Alpha k2. How much is derivative of k4? Alpha k3. How much is derivative of k1? Alpha k4. Yes. So there is this nice, so derivatives are easily written. Okay? So we have these functions. Now, for example, first of all, where are we? Please write down k1 at 0 equals 1, k2 at 0 equals 0, k3 at 0 equals 0, k4 at 0 equals 0. Why do I need this? Why it is nice property? Why is this nice property at all? That k1 at 0 equals 1, but then the rest equals 0. Because when I will be satisfying boundary conditions, just one entity will be staying alive. Just the rest will be 0. Okay, just one coefficient associated with k1. Whatever k1 is multiplied with, that will stay. The rest will be gone. So I every time deal with one function. Therefore, this guy did a very magnificent job of finding very nice set of functions. Now, not only that, w at 0, at x equals 0, then equals a1. Why? Because a1 times k1. k1 at 0 equals 1. The rest is 0. So therefore, w at x equals 0 equals a1. Do you get this? Now let us calculate the derivative, dw dx. So that is first derivative of k1, k2, k3, k4. So then the first derivative of w at x equals 0 equals alpha times a2. Because k2's derivative is alpha k1. k1 at 0 equals 1. The rest is 0. It's an awfully nice function he introduced. Then we can actually get also that second derivative. A3 equals 1 over EI. Maybe we don't need this A3, etc. So this is actually W equals A1 K1, A2 K2, A3 K3, A4 K4. Now derivatives. We wrote already. Derivatives are like this. K2's derivative is K1, K1's derivative is K4, K4's derivative is K3, K3's derivative is K2, etc. If I take only x without alpha, just K1x. K1x. Say it again? Yeah, without alpha. Just alpha is 1. So that is... So we start like, we write 4, 3, 2, 1, and then this circle, like they are connected like this. Now, m function's derivative, okay, equals m minus 1 function. Previous one. K2's derivative is K1, etc. So K1's derivative is, look, K1's derivative is K0, m minus 1. But this K0 is identified with K4. That is why I'm writing them together, like this. Okay, if I have alpha, then K1's derivative is alpha K4. This derivative then is etc., etc. So Professor Krylov or Krylov, whatever. That is how he introduced. This will be very helpful to us, it seems to me. These functions. Yes. And before finishing today's discussion, we do not go much further. I would like to talk about boundary conditions. What are the boundary? We should impose some conditions at the end of the beam. Okay, what are the conditions at the end of the beam? So pay attention. This is a simple support. Okay, simple support. Okay, maybe we start from here. Clamped beam. In the clamped end, displacement equals 0 and first derivative equals 0. Simple support. W equals 0, second derivative of W equals 0. What? Because this is connected with the moment. Bending moment equals 0. This thing here can rotate. Because it can rotate, therefore bending moment equals 0. Okay? I will write down this. Okay. Simple support. This means that this beam can move like this. So therefore there is no restriction on rotation. So bending moment mz we said equals EI d2w dx square. So this must be 0. Because if rotation is possible, then there is no restraint. So moment is 0. Moment is 0 means EI second derivative equals 0. But EI is not 0, so second derivative must be 0, as I wrote here. And we will continue discussion next time. And I assigned you the homework from the very beginning so that you will not be left without homework. And if you want to give me the homework, I will be taking it. Thank you. So you can put here.
For simple support, this one.
Yes.
The beam can move like
Yes.
this.
Yes. Like here. Rotate. Then I will sit down and